One thing that's rather interesting about acids and bases is that you have the textbook examples that, like what you saw in the previous videos about anything in the H at the front is typically going to be an acid, and anything with an OH at the end is typically, excuse me, going to be a base. And that's all very easy to recognize, but there are some compounds that can behave like an acid and behave like a base in the presence of something else. They don't necessarily look like an acid or a base, but they can take on the properties of an acid or a base. One very good example of that is our good old friend, water. Water, again, remember, is the same thing as HOH. Well, that's interesting because that looks like an acid, and this looks a whole lot like a base. Well, again, water is kind of an acid, and it is kind of a base. The fact is that it is a 1-to-1 ratio of hydrogen to hydroxide. Therefore, the pH would be equal to 7, which is neutral. So water, while it is neutral, can also act as an acid. It can also act as a base. Water is a very unique compound, as I hope you guys can appreciate this far into the semester. So what we're going to talk about now is what we call the Bronsted-Lowry conjugate pairs. Basically, we're going to have an acid and a base. Those will both be identified on the left side of the arrow as the reactants. And then on the right side, they're going to produce something which we are going to identify as their conjugate acid and a conjugate base. Let me go ahead and show you the example first before we get into the problems on the bottom. So what we have here, again, you guys should recognize NH3, that's ammonia. It's your window cleaner, and it is a weak base. Here we have water. Well, water can behave either as an acid or a base. So we don't really know what it is, but in this case, we do know how it's going to behave because we have a base. Therefore, this must act like an acid. Why? Because they're always going to be the opposite in these Bronsted-Lowry conjugate pairs. If you have a base, the other reactant must behave as an acid. Conversely, if you have an acid, the other reactant must behave like a base. They will always be the opposite, okay? The left two will always be the opposite. Again, we know NH3 is a weak base, therefore our water must behave like an acid in this reaction. Now, knowing that, what we have NH3, when it gets the proton by giving away its electron, it will become a conjugate acid. Why? Because we have one additional H. This one has one more H than this one. Therefore, this would be an acid, again, a conjugate acid of the ammonia. Conversely, we have H2O right here. Well, this has lost the H, so there was no H here, right? That is gone. Therefore, it's going to be the basic form. Again, that's not too surprising because it's OH minus, but the acid will become a conjugate base. So like I said before, these two will be opposite. These two will be the opposite. And this one, I'm just going to clear all that. The base will become the conjugate acid and the acid will become the conjugate base. Okay, so that is the pattern that you always want to follow. You will have an acid and a base on the left side. You will have a conjugate acid and a conjugate base on the right side. Never two acids and two bases or two bases and two acids. Always an acid and a base and a conjugate acid and a conjugate base. All we need to identify is what makes what. The NH3 looks like the NH4. Therefore, the NH3 is the base. It took on an extra proton or extra H. Therefore, the NH4 is the conjugate acid form of the NH3. The water, H2O, has lost the H, so it is the base. And then again, it's going to be a conjugate base as OH because, again, it has no H. It lost an H. It has one less. So let's go ahead and try this down here at the bottom. We have NH3, and we have HF. HF, this is hydrofluoric acid, and we have ammonia. This is going to be a base, and that's going to be an acid, but we're going to have to figure out what they're going to behave like. Again, this is where it's kind of weird. So NH3 is a weak base, and hydrofluoric acid is a weak acid, but we cannot have acid and acid. They will not act like that. One of them, if one is going to give a proton, something else must receive the proton, right? Therefore, again, that's the Bronsted-Lowry definition. Therefore, even though we have a weak acid and a weak base, one of them must act like something that wouldn't normally do. Again, because we have to have a movement of protons, according to Bronsted-Lowry. So in this particular case, what we're going to do is look at the right side. Maybe this will help. Notice this has lost the H, and this one has gained an H relative to this one. So we know, obviously, these are our pairs. That's pretty easy to identify, right? Because NH3 looks like NH4, and HF looks like F. But we need to figure out which one is the acid and which one's the base. So because this one has an extra H, then this one must be the conjugate acid, making this a base. And if this is the base, this must be an acid. And then therefore, it's lost the H, so this must be the conjugate base. In fact, that is a whole lot like our example up at the top of the screen. Again, it will not always be in that order, but in this particular case, it was. So to talk through that one more time, just to make sure you guys all understand, we identified the two pairs. NH3 pairs with NH4. HF pairs with F. Now, of those different pairs, one of those on the left has to be an acid and a base. By looking at the NH4, I noticed it had an extra H. Therefore, that makes it the conjugate acid, making NH3 the original base. On the right side, we have F. F has lost its H. Therefore, it has to be the conjugate base to the acid of hydrofluoric acid. All right, moving on to the next one. We have H2CO3, that's called carbonic acid, and water makes HCO3 and H3O+. H3O+, this is called hydronium. Oh, what am I spelling with a D for? Hydronium. This is a hydronium ion. H3O+. Okay, you're gonna see that a lot. H3O+, that's hydronium. If I ever say hydronium, it's H3O+. So what we have here is, this is going to be an acid because it's carbonic acid. Okay, and again, it also pairs with this one. And notice, again, this has one less H, therefore this is the conjugate base. Okay, H2O, water, ironically, is going to have to behave as a base because we already have a water on the left side of the equation. Therefore, this must behave like a base. And these two are a pair. Notice this one has an extra, it took an extra proton or extra H plus because it had two, now it has three. So that makes it a conjugate acid. Remember, just like in above, whichever one has more H's will be the conjugate acid. Last but not least, or I guess we have two more, excuse me. We have cyanide, HC, or my gosh, CN, and water makes HCN and OH. So this one's a little bit tough. We're going to have a HCN. This is going to be a acid because we have a H there. So that's going to be our conjugate acid. And if this pairs with this, then this must be our base. Interestingly, water is now must behave like an acid because remember, if we have a base, we must have an acid because we have an acid and a base on both sides of the equation. And again, if that is an acid, then this one must be its conjugate pair, and it is. Notice it has one less H, therefore it's going to be the conjugate base of water. All right, again, notice I'm always going from the first to the third and the second to the fourth. That is a coincidence. Do not always assume that my first compound in the equation will go to the third and the second will go to the fourth. That is actually quite a coincidence, and I kind of wish it wasn't doing that because I'd like you guys to see that in another case. All right, last but not least, finally, we have our water mixed with this compound that's called acetic acid. When I put those together, we're going to make vinegar. So here we have the hydronium ion and acetate. So again, unfortunately, this one goes with that one. This one goes with this one. Okay, so again, looking at this one, we have an extra H. This must be the conjugate acid, making water a base, which again is not surprising because I already told you this is acetic acid. Acetic acid, its conjugate, notice it has one less hydrogen. It's lost its hydrogen, so this must be the conjugate base of acetic acid. Again, just to repeat, you will always have an acid and a base on the left side. you will always have a conjugate acid and a conjugate base on the right side. We just need to figure out the order of those two. So what we do is we find the pairs. Which ones look similar? Excuse me. H2O and H3O look very similar. HC2H3O2 and C2H3O2 look very similar. So we find the pairs. Then we're going to compare the two on the left and the two on the right and the two pairs that straddle the arrow to figure out, again, which has more H's, which would be the acid, and which has fewer H's, or hydroxide, and that would typically be your base. Again, the pattern is relatively easy once you see it. You just kind of need to figure out what is what. That again is called a Bronsted-Lowry conjugate pair, where in the presence of each other, in that case, one will act like an acid and one will act like a base, even though they may not typically be an acid or a base, but in the presence of their other one, they will be one, okay? All right, guys, that's all about your conjugate base pairs.